So moving on from injections, surjections, and bijections with these very, very general functions, we start thinking about other things that we can do. So we've thought about subsets, intersections, unions, but because these functions are so general that we're still dealing with, we're not dealing with functions on sets of numbers. In particular, we're dealing with very, very general sets. So we don't know, for example, that we can add functions or subtract functions, divide functions, multiply functions, differentiate functions, because we're dealing with such general objects. And we want to stay dealing with these very general objects for the moment. And so but the only thing that we can do with these functions that we haven't considered so far is what happens when we do functions one after the other? How does that interact with the other things that we've been talking about, namely injections and surjections? So what happens when we compose two functions? Does that preserve some of these properties that we've been talking about? And that's the topic of this lecture. So compositions of functions. So first thing we should do is we should define them. So in particular, let's chain two functions together. Let's think about a function f that takes us from a to b and a function g that takes us from b to c. Well, we can put those together to make a new function g of f, which we just define as being, well, do f first and then do g. So a little bit more formally, if we have functions f taking us from a to b and g takes us from b to c, so remember the codomain here has to match the domain there, then the composition of those two functions f and g, which we denote by g little circle f, defines a new function, g little circle f, that takes us from a to c, defined by g of f of a is just g of f of a for everything here in the domain. That's why we have to make sure that the codomain here matches the domain there, because otherwise, well, we might have illegal inputs into our function g. Now, this is a new object, and we can start to think about what else it does. And one thing that's definitely useful to note, but a little bit painful to prove, so we won't do it here, is that function composition is associative. So that is h of g of f, if we do this composition first, is the same as h of g of f, where we do this composition first. So this associativity makes life a lot easier for us, but we won't prove it here because it's not very enlightening and really quite tedious. Now, when we do chain functions together like this, we can ask how does it interact with injections and surjections and bijections, these properties we defined in the previous lecture. So let's take f from a to b and g from b to c. Well, if f and g are both injective, then so is their composition. And if f and g are both surjective, so is their composition. And consequently, if they're both bijective, then so is their composition. So this is telling us that composition plays really nicely together with injection and surjection. These interact really well. And we can prove these properties, this interaction between composition, injection, and surjection, really quite easily. The proofs aren't very difficult. So let's take injections and show why it works. Well, let's use the injection definition of different map to different. So if we have different objects here in A, they're going to map to different objects in B, and then they're going to map to different objects in C. So let's take 2 points here in A that are different. Well, because the function f is injective, we know that the images of those points have to be different. That's what injective means. And since g is also injective, we know that the image of these different points will itself also be different. And so we know that a1 not equal to a2. Injectiveness tells us f of a1 is different from f of a2. And so g of f of a1 is different from g of f of a2. And so g of f of a1 is not the same as g of f of a2 as required, showing us that that composition, g of f, is also injective when f and g are injective. Now, for composition of surjections, we use the property that everything is mapped to by something, and we, instead of going forward, we're going to go backward to make the proof work. So let's take something here in C. Then because the function g here is surjective, we know there's something here in B that maps to that point C. So that is where there is a b in B, so that g of b is equal to c. Then since f is surjective, we know there's got to be something here in A that maps to that point in B. So there's some a in A, so that f of a equals b. Well, then we can just chain those things together to find a point in A that maps to that starting point in C. So in particular, g of f of a is g of b, which is equal to c. So for any c in C, we can repeat this little bit of reasoning to find something in A so that g of f of a is equal to c as required in order for it to be surjective. So if f and g are surjective, so is their composition. And then we've shown that a bijective function, which is injective and surjective, composed with another bijective function, injective, surjective, gives us something that is injective and surjective, and so bijective. Now, notice that if we flip back to this statement of the theorem here, that this tells us that if these are injective, then their composition is injective. If these are surjective, then their composition is surjective. So its logic is going in one direction here. And we can ask about the converse. So in particular, if we know their composition is an injection, what can we say about F and G? And if their composition is a surjection, what can we say about F and G? And we can't actually give a full converse here, but we can give a partial converse. In particular, if G of F is an injection, then F is an injection, but maybe not G. If G of F is a surjection, then G is a surjection, but maybe not F. And the proof of these statements make really good exercises, which maybe you'll get in homework or something similar to that. And also note that we've pushed this as far as we can, that you can't actually extend this to a full converse of the original statement. In particular, you can make functions f and g so that g of f is an injection, but g isn't. And that g of f is a surjection, but f is not surjective. Sorry, mistake there. Okay? So you can not push this any further to get a full converse. And the proof of that's not actually very difficult. You can make an example like the following. So that g of f is an injection, but g is not injective. G of f is a surjection, and again, that same mistake there. F is not surjective. So let's consider functions f and g defined by this diagram below. So I've got functions a, sets a, b, and c, and just to give these things names, I've set 1 and 2, 3, 4, and 5, 6 and 7, so we've got some handles on things. Well, then notice that g of f of 1, so here's f1 and 1 gives me 6, g of f of 2, 2 goes to there, 7, so different inputs here give me different outputs there, so g of f is injective, but notice here that g of 4 and 5 are the same, so g is not an injection. So that's this example here. And we can similarly cook up a way of showing that you can find function f not surjective to show that this indeed can happen. So here, notice that 6 here is g of f of 1, and 7 here is g of f of 2. And so g of f is surjective because I can find something that maps to 6, something that maps to 7. But there's nothing here that maps to 5. So even though f of 1 is 3, f of 2 is 4, there's nothing here that maps to 5, and so f is not a surjection. So I can find g of f is a surjection, but f is not surjective. And so these partial converses that I have back up here, when I gesticulate with my pointer here, or maybe with my finger, they can't be extended to full converses. Okay, and again, I apologize for a little typo in the slides here, and I'll fix that in the ones that I post online. Let's stop here.